sort of cures do we have? And people have, I mean, so the 70s was full of people who were selling you circuits that fixed the metastability problem, right? And it was sort of interesting to some of us, true believers, who said, well, you can't actually fix it. And they would go, no, 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 for 10 ducks, I got a solution. Comes with Ginsu knives. So I'm going to show you our solution here. I'm going to sell you the Ginsu knives in just a second. So it's the idea of this metastability thing is in the way from going from one state of a bistable system to another state of a bistable system, I'm going to pass through this metastable point, okay, which will eventually become resolved, but not in bounded time. In other words, if you give me a certain amount of time in which I have to make the system produce a digital answer, I can't do that. Okay, the recovery time is unbounded. On the other hand, the longer I give you to do it, the greater the probability is that the system will come out of the metastable state. Okay, so our strategy is we can't eliminate the metastable state, but we can introduce this delay. And we'll do it like this. So here's some circuits that we can put in, where we basically use these back-to-back flip-flops. So it's the first flip-flop that's going to go metastable. It's the one that the changes are are at a timing that are independent of the clock. So this flip-flop may go metastable. But it's not until the rising edge of the next clock that we're actually going to use this value coming out of the first flip-flop. So we've given it a whole clock period to become stable. Does that make sense? Now, there's some probability that it will still be metastable, and this flip-flop itself, because it's right at that, his input is right at that balance point, will then itself become metastable. Or this guy may be changing it some awkward way so that this clock edge will put this latch into its feedback loop just at the wrong moment. But there's an exponential decrease in that probability by making this delay. And in fact, the longer the clock period, the chances of this output being metastable drops exponentially. And in fact, if I go off and I'm still worried, I can add another layer of that. And so I'm getting these sort of exponential decreases. So if you have a system with a very, very high clock rate, in fact, you don't wait very long between the flip-flops. The clock edges are only a picosecond apart. But you can put a string of these flip-flops to get as long a delay as you want. And away we go. And nowadays, the modern system, because of the high gain and things like that, I mean, it turns out those time constants now are much smaller than the sort of 30 nanoseconds that I mentioned earlier. So, and so you can make this as small as you want, but you have to pay some price. That delay is inherent in coming up with a system where the probability of failure can be engineered to be as low as you want. You go to your boss and you say to him, her, whichever, and say, "Dear boss, with one chance of failure every year, is that good enough?" And they go, "No, no, our systems are reliable." So how about one failure every 10 years, every 100 years, every 1,000 years? And the boss says, thinks for a moment, says, "I'm not going to be here in 1,000 years. So maybe one failure every 1,000 years is fine. I won't expect the phone to ring." Okay, so the point is you can pick some probability of failure that you're comfortable with, okay, and engineer the time delay here such that the possibility of still being in the metastable state, this node going metastable, is very, very low. So this is what we call a pulse synchronizer. Okay, and pretty much everybody puts those on all the real-world inputs to their digital circuits. And you're right, there is a delay associated with that. That delay may now only have to be a couple nanoseconds to keep the probability of failure low, but you have to pay that delay. So does that answer your question a little bit? So yes, if I have real-world inputs, I have to put in my time budget. I won't be able to process, though there'll be a delay before I process them with my synchronous system. Typically that delay is small enough that it does, real world inputs, the timing tends to be, even if you're having an auto wreck, right, your car has the front of your car has just hit the bridge abutment and now you want to deploy the airbag and you have this little computer that's going to decide when that's to be. And so you have the analog sensor input with the accelerometer suddenly going, whoa, I'm accelerating or decelerating very quickly. Okay, and you have a little computer that's running on a couple megahertz clock inside to say, deploy the airbag. The point is that it can reliably make that decision within, nanoseconds or maybe a millisecond or two, and the car doesn't crunch that fast. Right? You have several milliseconds to deploy the airbag before the person actually reaches the windshield. So in the real world, these sort of delays that we can do with modern electronic systems are very fast compared to the sort of things that we're trying to deal with. Okay. So what can't we build? So the key word is bounded time. We can't build an asynchronous arbiter, decide which edge came first in bounded time. So poor Alex Trebek may be just out of luck. Okay, as he runs his Jeopardy show. And, if he sits there and goes, you can say, aha, metastability. He's going metastability. We can't build a bounded time synchronizer. So basically, we have an asynchronous input to our flip-flop. It may go metastable. Okay, and these are all different variations of the same theme, right? We can't, for instance, map a continuous variable into a discrete variable, okay, over the entire possible input range, okay, in bounded time. We can't build a circuit that actually does that.